Hey everyone, in today's lesson we're going to be looking at radioactive decay and the different types of radioactive decay and kind of how that all works. So to begin, we're going to take a look at this particular diagram, and I also want to talk about a few of the researchers that were heavily involved in the discoveries of radioactivity and radiation. Essentially, radiation and radioactivity was defined by three pretty well known names, but if you don't know them, I'll bring them up here. They each won the Nobel Prize for their work in radioactivity. And the first is Marie Curie and her husband, Pierre Curie. Oh, just a second. Pierre Curie here. And then finally Henry Becquerel. Now, these three all won the Nobel Prize for their work in radiation and went on to further studies. I'll just note that these three certainly gave us a lot of insight into how atoms and elements work. In fact, actually discovering a couple of the elements, and I haven't read into everyone in depth, but I do know that Marie Curie died sometimes later of leukemia, most certainly as a result of her work with radioactive particles. So that being said, we want to go into kind of what they were looking at. So let me bring back the paper here, and radioactive decay or radiation kind of works in three different modes. And so we have three kind of lines drawn here. And so it was defined as alpha, beta, and gamma radiation. So we have alpha radiation, beta radiation, and then gamma radiation. And so the three types of radiation work a little bit like this. This is their trajectories if they were set within an electric field. So gamma radiation just goes straight through. It doesn't deflect one way or the other. From that, we can tell that gamma radiation is neutral. It has no charge. Alpha radiation gets deflected essentially opposite of beta radiation. So alpha is positively charged and beta radiation is negatively charged. And so the work of scientists in the early 1900s, including the three that we talked about, allowed us to define these three types and really look at what they are. So the first we'll talk about is alpha radiation. And if we recall from our last video, we've seen alpha radiation before. Alpha radiation is defined like so. It is something like uranium-235, 92, changes into thorium-231, 90, plus helium-4, 2. Okay, so the alpha radiation that we see is the ejection, the emission of a helium nucleus. Okay, so when we talk about an alpha particle, we were talking about a helium nucleus. And so this is kind of where those alpha particles that we've been using for quite a bit of time for problems or for calculations originate from. The helium nucleus is a type of radiation known as alpha radiation. When we talk about radioactive decay and radiation, there's a few things we have to actually keep in mind, and that's why having these here written in this notation is really, really useful, because there has to be a few things that happen. There has to be conservation of charge that occurs within all types of radiation. So charge is always conserved. It's a conserved quantity in physics. And so if we look here, we can see that charge is conserved because before we had 92 protons. So we have a plus 92 charge, and after we have 90 plus 2. So we still have a plus 92 charge. And then you also have 231 plus 4, that's our 235. So like your mass is also conserved here. Okay, so that being said, that really is alpha radiation. And the second type of radiation is the beta radiation. So beta radiation, or beta decay. So the example for beta decay occurs in a carbon-14 atom. Carbon-14 atom does this. Nitrogen 14(7) plus that beta particle plus this other guy. And no, this is not that. So I just have to actually draw this a little better. There. With a little bar overhead. Okay, so this is beta decay. Alright, so first and foremost, there's a little bit more that we have to talk about with the beta particle. But I just want you to know that I'm not going to forget about this, but I will ignore it for right now. If we look here, we have to have conservation of charge. So before we had 6 protons, and now we have 7 protons. So what needs to happen here is, well, this has to be a negative. So that's what kind of one of the ideas is. It deflects in the opposite direction as alpha radiation. Conservation of charge puts that beta particle as a negative. A negatively charged particle, and you want to look at this as well and say, okay, I had 14 nucleons before. So if I look at this, I had 6 protons and 8 neutrons, and now I have 7 protons. Do I still have 8 neutrons? No, I have 7 neutrons now. That 14 number did not change. Okay, and this helps us define what beta decay is. And if this is 14 and that's 14, this is 0. Alright, and that's sometimes how we draw a beta particle. Okay, and so beta radiation is defined as a neutron changes into a proton and a beta particle. A beta particle. Well, what is that beta particle? What do we know that exists that basically has no mass and a -1 charge? Turns out your beta particle is an electron. Okay, so that is beta radiation. Okay, well, it's kind of one type of beta radiation. The other way beta radiation happens is a little bit weird, a little bit different, and kind of works a little bit like this. Say you have nitrogen 13 and 7. This is going to change into carbon 6 and 13. Okay, this almost seems like the reverse operation here. So here you had 7 protons, now you have 6 protons. So what we think happens here, we think happens is a proton changes into a neutron. Okay, so that kind of makes up for most of the conservation of mass, but we do not have conservation of charge. Okay, so we have to have another thing here, right? A proton just changed into a neutron. So we've lost positive charge. So we end up getting as a beta particle, but it's a +1 now. It's also 0. And then we have this guy here. I feel very bad that we're not talking about him, but we'll make sense of it in a moment. A proton changes into a neutron, and a beta plus particle. Okay, so just before we continue, there seemed to be this other type of radiation that basically went like this. And this was referred to as the beta minus particle, and this was referred to as the beta plus particle. And, well, they're kind of the same thing, but they're a little bit different. See, this is almost like, if this is the electron, this is kind of like the electron if it had a +1 charge. And this was a thing that was predicted mathematically, but took a little while to see. This right here is known as a positron. Okay, so basically with your beta radiation, whether it be beta minus decay or beta plus decay, those are 2 different types of beta radiation, you get about 3 weird things, okay? Knowing that this is an electron isn't that weird, but now you get a weird thing called a positron, and then we have 2 things we haven't actually talked about yet. But you get a beta plus particle or a positron. And you also get these 2 things, but before we talk about those, a positron is defined as, I'm gonna write this maybe up here, just as a side note. A positron is the antimatter counterpart. Antimatter counterpart of the electron. It is now at this stage of physics that we can talk about antimatter. So the brief idea is that the positron has the exact same mass as the electron. It, however, has the exact opposite charge. It is referred to as the antimatter counterpart of the electron, and I want to just, because sometimes when we talk about antimatter, you go into the idea of, does it have negative mass? No, it has normal mass. It's an electron, but it's positively charged. Electrons aren't positively charged. So you have this oppositely, it's very symmetric in a way, thing that is the exact same size as the electron in terms of mass, but the opposite charge. So positron is the antimatter counterpart of the electron. The cool idea of the positron is if the positron comes into contact with any electron ever, both of them are wiped from existence, and you get a little bit of energy that comes off. So, yeah, that's cool things about physics. So positron, antimatter, electron, normal matter. Now, what we have is to talk about these two things. So this little guy here is actually little. It's referred to as a neutrino. It's essentially the idea that it's just a little bit of like a counting error here, and so you had to have this other thing called a neutral particle because charge is already conserved and known as a neutrino. So this is a neutrino, and this is an anti-neutrino, the antimatter particle of a neutrino. So we're getting into some pretty wild stuff here, I think. But antimatter exists, and so that's what these two things are. They're just very, very small neutral particles, if that makes sense. Our answers lead to more questions. But I digress. Now we look at the last type of which is gamma radiation. It's weird. Okay, so we have gamma decay. Gamma decay kind of starts off, we're going to start it with beta minus decay. So we're going to just kind of see how this happens. Let's take the boron 12,5 atom, and we're going to beta decay it. This would be an interesting thing for you to try and figure out what actually happens afterwards. You can pause the video right now. Try that on your own. We're back, and we have carbon 6 and 12 plus a beta minus 1 particle plus an anti-neutrino. So that's basically the beta decay process for a boron, where a neutron changes into a proton and an electron. But you have this, and this was something that's a little bit new. I put a star beside it. The star is defined as the nucleus has a lot of energy. The nucleus has a lot of energy, and so it would like to shed that energy. It wants to get rid of that energy, and so it kind of does this. And this is the gamma decay. That 12 carbon 12,6 with the star, meaning it has a lot of energy, is going to decay into carbon 612 plus a gamma particle. Okay, so essentially when some processes of radiation happen, the nucleus that's left over has quite a bit of energy, and so it gets rid of that energy by undergoing gamma decay. And this is a gamma ray photon. So the photon is the particle of light. It's a gamma ray, so it's a photon in the electromagnetic spectrum of gamma rays, and so it has a lot of energy. It's also neutral because photons are neutral, so that's why we got this description here. So I hope that makes sense. So that's gamma ray photon. Okay, so I want to talk a little bit about a few different types of other concepts. The first thing we're going to talk about is actually um, blocking radiation. So things undergo radiation, and we have to know a little bit about them. So we have alpha, we have beta, and we have gamma. And these are referred to as ionizing radiation. And so we have to kind of take a step back and think, okay, this emits a helium nucleus. And this emits either an electron or positron. So you have a beta minus particle or a beta plus particle. And then this is actually just like a high energy photon. So there's a reason we call these ionizing radiation. And it's because it's because the first two are charged, and then that's basically going to have problems if it interacts with like life in general. So if it interacts with any type of organic material, it's capable of throwing off the balance of neutral molecules or literally neutral anything that's a biological structure. And so when you do throw off that balance, you basically are inhibiting or screwing up a biological function. Many of these biological functions rely, I suppose, on the neutrality of the molecules. And so when these two things come into play, and even the third one here, although you might have to think about it a little differently, as soon as you throw off the balance of something, like just take, for example, the positron. The positron comes into contact with an electron of a molecule and annihilates it, and then sends off some extra energy. Well, that molecule is now ionized. It's now an ion. And so now it's going to start to behave differently. And that causes big, big problems. I hope that makes sense. And that's basically how those two work. And then the high energy photon, I'd like for you to kind of recall, because this is how I think about it, the Compton effect. Remember when Compton basically flung a bunch of X-rays at things and figured out that he could strip the atoms of their electrons? The gamma ray photon has the ability to do that as well with biological life. So it can actually just completely come into a molecule and it'll work a little bit differently, but it will give the electrons within the energy levels of those atoms, of those molecules, the ability to just be completely flung away from the molecule, and they get stripped away, and then you have ionization that has occurred. So the high energy photon can just ionize things, essentially the same idea as the Compton effect. The Compton effect was using X-rays on metal. The high energy photons can basically do the same thing with flesh. Okay, I hope that makes sense. So that's some things. So now we want to figure out how to not have that happen to different types of organic matter. The way it's defined is alpha radiation has the least penetration. And alpha radiation can be stopped essentially by a piece of paper. Yeah. yeah, like a thin sheet of paper can stop an alpha particle from getting into something that's organic. So paper can stop it, like your clothing can stop it. So if there's an alpha source around for some reason, your clothes will be able to stop the penetration of the alpha particle. The beta particle has, I guess, it's not the least, it's not the most, I guess it's the medium size of penetration. Beta particle gets stopped by aluminum. So, like tinfoil will stop a beta particle. And aluminum will also stop an alpha particle. Like, that's kind of the idea. So, the last being the gamma particle, and this is the highest penetration. And you can stop this with lead, but that's the best thing that there is, stopped by lead. And if this is a very continuous source of gamma radiation, make it very thick. That's basically the idea. Now, the lead will also stop the beta radiation. So just kind of, those are the ways that you stop radiation, the ways that we've developed to stop radiation. So that being said, we'll move on to a few other concepts before we end the video. Alright, so the first one is the half-life. Okay, and so there's kind of a mathematical formula here. N is equal to N0 and not 1/2 to the power of T over T 1/2. Okay, so let's define all of these. T is the time that has passed. T 1/2 is what's referred to as the half-life. N is the amount, and N naught is the original amount. And when we talk about amounts, we're talking about the amount of material that is remaining. So, for example, we know that carbon 14(6) undergoes beta radiation to 14(7) nitrogen plus the electron plus the antineutrino. So the idea is that each and every element undergoes, each and every kind of isotope, I should say unstable isotope. There are some things that are stable, there are some things that are more stable than others, but everything undergoes some type of decay, and it does so at a particular half-life, and this is represented as the time it actually takes for the element to be half of the amount it started at. So that's the idea of the half-life. So for example, let's say you started with 1 kilogram of carbon-14. The half-life of carbon-14, this guy's half-life, is, I believe, 5,780 years. I'm going to double check that. But that's the half-life. And so you can think of pretty well that 5,780. I'm seeing that's within range. It's give or take a little bit, but we can say a little more accurate would be 5,760. Okay, so within that amount of time, so essentially after 5,760 years, there will be half of the 1 kilogram remaining. So there will be 0.5 kilograms remaining. And then after another 5,760 years, there would be 0.25 kilograms remaining. And then after another 5,760 years, there would be 0.125 kilograms remaining. And that's kind of how half-life works. So it's not that everything decays in this amount of time. It's that that's the amount of time it takes for half of the amount to be remaining. So another example, it's all kind of relative, but we looked in the last video, uranium-235, 92. That undergoes alpha decay. So I say alpha particle 42 plus the thorium-231, 90. That has a half-life of 708-ish million years. So if you had a kilogram of that uranium-235, after 708 million years, you'd have half a kilogram of the uranium-235 and roughly just under a half a kilogram of thorium-231. I hope that kind of makes sense. That's kind of how half-life works. I'll show you a little bit of how to now kind of work with a little bit of the math that we've been using, actually work with this particular equation, because it's an exponential, and that's a little bit new. So the one way I can encourage you is through our trusty Desmos graphing calculator. Let's get 30 level out of the way. And let's just take the carbon-14. So the amount that we have, we'll call that N, is equal to the N naught amount. So let's say we start with 1 kilogram of carbon-14. Half represents the fact that this is after so much amount of time, half of it's remaining, and then we raise it to the power, so it's an exponential. I want to make sure that's clear. It's kind of hard. So 0.5 raised to the power of T over 5,760. So we got to change our scale a little bit. It's going to take a long time, and so that's actually on the x-axis, and it's going to take thousands and thousands of years. So let's actually say 30,000 years, and we'll go up by 5,000, and we'll say the axis is -2. Doesn't matter. 2 also doesn't matter, but fits everything in here. So the curve of every single half-life equation kind of looks a little bit like this, and so you can basically plot that whole thing for however much amount is there. You know, if we had 3 kilograms to begin, we just start at a different place, and after so many years you're going to have half of it left. After this many years, actually, the 5,760. So let's actually see if we say T is equal to 5,760. We'll go X is equal to 5,760, so we can get that nice intersection. We'll make this a different color because I feel like it. And after 5,760 years, if we started with 3 kilograms, after that many years, we'd have about 1.5 kilograms, you can see there. And so after maybe 2 times that many, 11,525, we'd have half of the half. So half of 1.5 is 0.75. And so you can kind of use this to determine how much you would have left after a certain amount of time. The other way we can ask questions, how long would it take for you to have so much left? So imagine that we said we had how long would it take for you to have 0.375? So then we can graph it like this and find the intersection point. Well, it would take 17,280 years, which happens to be about 3 half-lives. That's actually 5,760 times by 3 to get 0.375 kilograms. One thing you'll also note, and this kind of comes into play from our math courses, but this is kind of an asymptote. You're never going to get rid of all of the actual material. You'll always have a little bit more left. So you're down to a single atom, of course, in which case that would, after so long, decay away to having nothing. So it's mathematically an asymptote, but like physically, you could have one atom remaining. So that being said, the other thing you can do is imagine that you're asked to solve for when there's 10% left. So 10% of the original amount. So what's 10% of 3? Well, that's 0.3. And we're saying, what's the intersection point? You'll notice that this is not a very nice decimal number, and this is how we would kind of look to solve that mathematical equation using graphing methods. So Desmos is your friend in this case. That being said, that should be everything you need to know about radiation and radioactivity and half-lives, and hopefully you're understanding things. Until next time, I think what we're going to look at next is nuclear fission and fusion. So hopefully that's fun and relevant.